Hi everyone, today we'll be looking at the statistics paper of June 2018. So first question says that Helen believes that the random variable C representing cloud cover from the large dataset can be modeled by a discrete uniform distribution. Keyword here being the uniform. So that means that all possible outcomes carry the same probability of happening. Write down the probability distribution for C. Well, if we have some knowledge of the large data set, we know that cloud cover is measured in octas. So this means that it takes integer values from 0 up to 8. So what we are expected to say here is simply that if C is a random variable, and this is the probability of capital C being C, the values are 0, 1, 2, 3, 4, 5, 6, 7, 8. Because we've got 9 possible outcomes, each of them being equally likely, that's 1 over 9. So this is like the proportion of the sky of the celestial dome that it's covered by clouds. And B, using this model, what's the probability that cloud cover is less than 50%? Well, if we are measuring this in octas, the probability of being less than 50%, less than half, is anything up to 3. So the probability of C being less than 4 is simply the probability of C being less than or equal to 3, which is 4 over 9, because I just added up these 4 values. Now, Helen used all the data from the large dataset in HERN in 2015, finding that the proportion of days with cloud cover of less than 50% was actually 0.315. Well, that's the experimental probability here, and if you compare it with the actual probability, the 4 over 9, okay, we are asked to comment on the suitability of this model. So we are expected to say that the probability of 0.315 is less than what is suggested by the model. Hence, model is not suitable. If we were to be dealing with a good model, we would have expected close agreement, not necessarily identical, but close agreement between what we observe and what we predict based on the model. Suggest an appropriate refinement to Helen's model. Well, a possible refinement would be not to use a uniform distribution, so use a non-uniform distribution. Because the fundamental assumption behind Helen's model was that all values were equally likely, and this is probably not the case. So use a non-uniform distribution, a distribution where some values maybe are favored more than others. That was question 1. Moving on to question 2, we've got Tessa owning a small clothes shop in a seaside town. She records that the weekly sales figures, W pounds, and the average weekly temperature, T degrees Celsius, for 8 weeks during the summer, leading to a PMCC, product movement correlation coefficient, of negative 0.915, stating the hypothesis clearly and using a 5% level of significance. Test whether or not the correlation between sales figures and average weekly temperature is negative. So we need to make sure that we are setting up the hypothesis test in the right way. Our null hypothesis is always one of no correlation, and it's being suggested that the correlation is negative. So we have a one-tail test, H1 rho is less than 0, and we set our significance level to be at 5%. Now, based on the sample of size 8, so n is 8, we got R to be minus 0.915. Now, if you look in the formula booklet, the critical value, so you just look at the table of values, and the critical value is minus 0.6215. A nice way of considering whether you should be rejecting or not is to draw a bell-shaped curve, and minus 0.6215 is here, and you've got the observed value being well into the critical region. So I'm just gonna say that minus 0.915 is less than minus 0.6215, significant, reject H naught. And we need to state a conclusion in context, so evidence of a negative correlation. Between, and we just need to state the two variables, it's the weekly sales and the average weekly temperature. Now, a couple of things to notice here and be careful with. You have to use a letter rho. If you use R, you will be penalized. Okay? And also, we always give a conclusion in context to finish off the hypothesis test. B, suggest the possible reason for this correlation. Now, we really need to think on a practical level here. She's owning a small clothes shop in a seaside town. So, seaside town, and we've got temperature increasing. As temperature increases, the weekly sales go down. So it could well be the case that people go to the beach instead of the shops. So we just could say that as temperature increases, more people spend time on the beach. Thus, sales decrease. C, Tessa suggests that the linear regression model could be used to model this data, and we need to state, giving a reason, whether or not the correlation coefficient is consistent with Tessa's suggestion. Now, the product moment correlation coefficient measures the extent of a linear association between the two variables. The closer we get to the two extremes, the -1 and the +1, the more evidence we have in favor of a linear model, of a straight line fitting through this scatter plot. So we can say that minus 0.915 is close to -1. There is strong linear association. I could say the word negative as well. There is strong negative linear association. Hence, a linear model is appropriate. And D, We are being given the calculated regression equation and we need to give an interpretation. Now, the gradient of a straight line is the change in y for every unit increase in x. We've got a negative gradient here, which means that for every extra unit in t, w decreases by 171. So we need to put this in context and actually say that for every extra degree Celsius, weekly sales drop by 171 pounds. It has to be in context. It has to be in context. Do not refer to W and T, refer to the variables themselves. 3, we have an experiment. A group of children each repeatedly throw a dart at a target. We've got random variable h representing the number of times we actually hit the target in the first 10 throws, and p that is modeling h as binomial 10, 0.1. So what are the two assumptions we're making here? Well, we are assuming, so p that is assuming that the probability of hitting the target is constant, and the throws are independent. Now we know that there are 4 conditions for the binomial distribution, but really the important ones is this assumption of constant probability of success and then independence of trials. Do not mention the fixed number of trials and whether it's a success or failure, only because we can easily check that these are valid. The assumptions are these two, and be careful to give them in context as well. And B, using Peters's model, find the probability of H being greater than or equal to 4. It's time to use my calculator for this one. So probability of H greater than or equal to 4 is 1 minus the probability of H less than or equal to 3. Now I need to be using my calculator binomial CD mode. I need to make this working on the probability to be compatible with the calculator. This is 1 minus 0.9872, which is giving me an answer of 0.012823SF. C. For each child, the random variable f represents the number of the throw on which the dart first hits the target. So we've got a new variable here, f, which represents how many trials up to and including our first hit. Using Peters's assumptions, so independence of trials and constant probability of success, what's the probability of f being 5? Well, the probability of f being 5 means that the 5th throw is the first time we hit the target. It's the probability that 4 first throws missed and the 5th one was a hit. Now, she's assuming that the probability of hitting the target is 0.1, so the probability of missing the target is 0.9. This is 0.9 to the power of 4 times 0.1. If you put this on the calculator, you get 0.0656. Now, Thomas assumes in this experiment no child will need more than 10 throws. for the dart to hit the target for the first time, and he's modeling the probability of f being n according to this, and we need to find the value of alpha. So f is how many times up to and including the first hit. So first of all, we need to realize that f attains the values of 1, 2, 3 up to 10, because I will surely take at least one throw. I might be lucky or able and hit from the first time, or take it until the very end to hit in the very last attempt the target. So I could actually come up with a table here. I have n, and here the probability of f being n. I could put the values 1, 2, 3, 4, 5 up to 10. And we see that for n is 1 is just 0.01. For n is 2, it's 0.01 plus alpha, then 0.01 plus 2 alpha. And this really forms an arithmetic sequence. It's an arithmetic sequence with first term 0.01, common difference is alpha. Notice it's an alpha, not a. We've got 10 terms, and we know that the sum of these first 10 terms is 1, because we are certain that one of these 10 outcomes will be observed. So I will simply do n over 2, so 10 over 2. I'm using the formula for the sum of an arithmetic sequence, and I have 2a plus n minus 1d. This will lead to an equation in alpha. So 1 is 5, I have 0.02 plus 9 alpha. 0.2 is 0.02 plus 9 alpha. 0.18 is 9 alpha, so alpha is 0.02. Okay, so somehow they managed to squeeze in sequences into a statistics question. That was part D, finding alpha. And then using Thomas's model, find the probability of f being 5. Well, because we now have the model and the value of alpha, the probability of f being 5 is simply 0.01 plus 4 alpha, which is 0.01 plus 4 times 0.02, which is 0.09. Just a mark for this one. And f, explain how the two models differ in describing the probability that a dart hits the target in this experiment. So we need to compare the two models. And we need to bear in mind that we have calculated the probability of f being 5 under both models. And for Peters's model, we got an answer of 0.0656, whereas for Thomas's model, we got an answer of 0.09. At the same time, we know that one of the fundamental assumptions behind Peters's model is that the probability of hitting the target is constant. So we could write that under Peters's model, the probability of hitting the target is constant. While under Thomas's model, this probability increases with each attempt. Because you get a higher chance for probability of f is 5. So what's really happening here is that Thomas's model is incorporating practice effects. You get better, and eventually you have more chances of hitting the target. So that was the last part of this question. Moving on to number 4, we've got Charlie studying the time it takes members of his company to travel to the office. So he stands by the door from 8:40 to 8:50 in the morning and asks workers as they arrive how long their journey was. State the sampling method Charlie used. This is a classic example of convenience or opportunity sampling. Okay. And then B, we have to state and briefly describe an alternative method of non-random sampling Charlie could have used to obtain a sample of 40 workers. So he could have used quota sampling. Quota sampling, and for example, he could have taken 4 people every 10 minutes. So he's expanding the time frame over which the sampling takes place. Other ideas could be for Charlie to actually split the data, let's say, into different ranks. Maybe you could have managers and then ordinary employees, and take 25 ordinary employees and 15 managers just to have the 2 quotas filling in. It will still be a non-random sampling method. C, Taruni decided to ask every member of the company the time x minutes it takes them to travel to the office. So the fact that we are asking every member means that we are looking at a census. That's the data selection process that's being used here. Census, when everyone is accounted for. And D, we've got the box plot summarizing results here. We need to write down the interquartile range for this data. Well, it's good to know that in a box plot, this is Q1, this is Q3, this is Q2, and actually the width of the box is the interquartile range. You can see that Q3 is 58 and Q1 is 26. So 58 minus 26 is 32, and that means do not forget the units. E, calculate the mean and standard deviation for this data. Well, we need to bear in mind that the basic summary stats have been provided. So the mean will be sigma x over n, which in our case will be 4,133 over 95, which is 43.5 minutes. And the standard deviation it's the square root of the average of the squares minus the square of the average. So this will be 202,294 over 95 minus 4133 over 95 squared. Do not use the rounded answer from the mean we found before. just use full accuracy. This is 15.4 minutes. F, state giving a reason whether you would recommend using the mean and standard deviation or the median and interquartile range to describe this data. Well, it depends really. We know that the mean is used in the absence of extreme values. Now we have two values here around 120 which have been identified as outliers. Okay, so we just need to say that data has outliers. These affect the mean and standard deviation. Hence, use the median and the quartiles. So you have to think of the mean and the standard deviation as going together as a description of location and spread, and they are used if you don't have any extreme values, if your data is symmetric, and in case you've got extreme values, then you go for the median and the quartiles. And Rana and David both work for the company. They have both moved house since Tyrone collected her data. Rana's journey has changed from 75 to 35 minutes, and David's journey has changed from 60 to 33. Now Tyrone drew her box plot again and only had to change two values. Explain which two values must have changed and whether each of these values has increased or decreased. So if you look at what's happening here, we've got a value of 75 becoming 35 and a value of 60 changing to 33. Okay, so if we draw the box plot again, we only have to change two values. Okay, so if you think about it, the 75 and the 60 were both above Q3, and these two values will become 35 and 33 respectively, so they will both go somewhere here. Okay, this means that we will have more values below 40 now, so that's part G. More values below 40 than above it. So it has to be the change that both Q2 and Q3 will be lower. Okay, because if you look at the box plot again, you'll have the new values at 33 and 35, so it means that we'll have to get the Q2 and Q3 to be lower down. Okay. Number 5, it's the lifetime L hours of the battery. Normal distribution mean 18, standard deviation 4. We've got a calculator that requires 4 batteries and will stop working when any one battery reaches the end of its lifetime. So find the probability that the randomly selected battery will be lasting for longer than 16 hours. Well, if L is the lifetime, we have just been told that L follows normal distribution with parameters 18 and 4 squared. And if we want the calculator to last for at least 16 hours, we want all 4 batteries to last for more than 16 hours. So we need to raise that to the power of 4. This is 0.691. I'm using the normal CD mode on my calculator. At the start of her exams, Alice put 4 new batteries. She has used her calculator for 16 hours but has another 4 hours of exams to sit. What's the probability that her calculator will not stop working for the remaining exams? This is a classic example of conditional probability. We know that on average, this battery will last for 18 hours. So we're just modeling one battery here. And we know that we have been in this exam for 16 hours. So we're certainly gonna see something here at some point. And we've got another 4 hours ahead of us. So we will finish the exam at 20 hours. And this is the probability that the battery will fail after the 20 hours. So the probability the battery will last for at least 20 hours, given that it lasted for at least 16 hours, is simply the double shaded, the intersection over the single shaded. So it's the probability of L greater than 20 over the probability of L being greater than 16. That's the probability of a single battery lasting for more than 20 hours, given that it already lasted for at least 16 hours. This is giving me an answer of 0.44621. It's not my final answer because if we want the calculator to keep working, we need all 4 of them, all 4 batteries, to do the same thing. So we will do 0.44621 raised to the power of 4, which gives me a result of 0.0396, which is the probability required. Alice has 2 new batteries, so after the first 16 hours, although her calculator is still working, she will randomly select 2 of them and replaces with 2 new batteries. What's the probability her calculator will not stop working for the remainder of her exams? We need to show that this is 0.199. So in this particular scenario, we've got 2 batteries that have already been there for 16 hours and we want them to last for another 4. So probability of L greater than 20 given L greater than 16. We've got 2 of these, so it has to be raised to the power of 2. And then it's the other 2 batteries, brand new batteries. We're just going to turn them on now. So we want them to last for at least 4 hours, which is the remaining time of the exam. And I've got 2 of these, so this is to the power of 2. So this is 0.44621 blah 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 raised to the power of 2 times 0.99976 blah 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 raised to the power of 2. Do respect full accuracy here, and you get the result of 0.199 as required. So you really need to have an understanding of what's happening here. 2 new batteries, 2 old batteries, all 4 of them need to be working after the 4 hours. So that's why I'm raising to the power of 2 and to the power of 2 respectively. D, we've got after her exams, Alice believing that the lifetime of the battery is actually more than 18 hours. She took a random sample of 20, finding the mean to be 19.2. We need to state our hypothesis clearly and test at the 5% level Alice's belief. So a classic example of a hypothesis test on the mean. So I start by writing down my null and alternative hypothesis. Mu is 18. Alice believes that mu is greater than 18. My alpha level is set at 5%. We know that n is 20, and we found x bar to be 19.2. We know that under h naught, x bar follows normal mu sigma squared over n. Sigma remains the same. And you can either do it using the p-value approach or the critical region approach. I'm actually going to do both of them here. So we're looking on the right hand side. This is the critical value here, and this is 5%. So if I call this C, the probability of x bar greater than C is 0.05. I can use my calculator for this one. I just need to say that the probability of x bar less than C is 0.95, and I get a critical value of 19.5. So this is 19.5, which means that the critical region is anything greater than that. The p-value approach will be one that uses the observed sample mean and inherits the inequality direction from the alternative hypothesis. We have the probability of x bar greater than 19.2, which is easily calculated with a calculator at 0.0899. This is greater than 0.05. Okay, so whatever approach you decide to use, the only thing that's missing is the conclusion. So we say not significant, do not reject H naught, and in context that will mean that we have insufficient evidence to support Alice's claim. So once more, be careful how you write your null and alternative hypothesis, and that you really need to have a conclusion at the very end. So that was the statistics paper of June 2018. Thank you very much.